Okay, let's now look at the distributed failover behavior of our scenario. We're first going to inspect the restate cluster. We're using the restate cdl command. What it shows us is that we're running a 3-node cluster, nodes 0, 1, 2. We've named the nodes US East 1, US East 2, US West 1, based on the region they're placed in. They're listening to an address that is in the local VPC, but the VPCs are appeared and the nodes talk to each other. We can see here that the log configuration for that cluster contains 24 log partitions. The sequencer here tells us which node is the leader for each of the partitions. So we can see for some of the partitions, node 0 is leader. For some of the partitions, node 1 is the leader. And all of the partitions place 3 copies on node 0, 1, and 2. If you have a larger cluster, the node and the copy set for each of the partitions would be different. But since this is just a 3-node cluster, each partition is replicated to all of the 3 nodes. Below, we're seeing the configuration of the partition processors, which are the workers, the ones that consume the events from the logs and that trigger invocations, update state, handle journal entries, and so on. And we can see there's always 3 partition processors for each partition, out of which one is leader and one is follower. And they're placed always on node 0, 1, and 2. So we're basically replicating the log, but also the followers and the indexed state to each of the 3 nodes and the 3 regions in this setup. Again, you can see the leaders are spread between nodes 0, 1, and 2. So all over the cluster, we have a pretty balanced setup here. Now let's run a few orders against our distributed setup. All right, let's issue a single order first that sort of hops between regions. So we can see it goes through the sequence of creating an order and adding a few order items. And some of these calls go to West 1, some of them go to East 1. This script here, it has an artificial delay. The backing services add a second for each order item. So that gives us later a chance to actually, trigger failures while these execute. If we didn't have the delay, it would actually be too fast to really go through meaningful failure observations. So these scripts also verify the correctness of everything that happens on the restate side, on the server side. So they're making the requests to West and East 1, but they're also fetching state back and verifying that everything actually is as they intended it to be based on the sequence of commands that they sent. Also remember, we have the verifying service in the background that implements the inventory asset tracking and the order status tracking. So this actually verifies as well that things are consistent. We would see errors if we ever see a consistency violation. All right, so we can see actually one order goes through the system pretty well, even though we're targeting hopping endpoints between East and West, and there's no unexpected sort of state caused by something like an async replication window or so, where hitting East after hitting West would actually mean East doesn't see still outdated state, and then we're writing to East and we have sort of like last writer wins and lost update scenarios. Nothing of that happens here. Let's make this actually even more challenging. So we're now triggering 2 parallel orders or 2 parallel clients for the exact same order, always trying to do the same operations against East and West. So we're seeing this one is actually calling create on the order on East. This one's calling create on the same order on West. One will always understand the order was opened through the request, and one will actually get an error that says order was already opened. Then both of them will add an order item, and both of them will see both order items in the list. So in this case, we added some US dollar and some Vanguard ETF. Both of them see the same thing. Now comes one of the crucial points. One of them will always try to execute the order, while the other one will cancel the order. We're sending those requests concurrently. So it's really a tricky race. Like whichever one hits restate first will sort of order before the other. Even in such a situation, if one of the clients says, I want to cancel the order, ultimately the order should be canceled. The question is just, does the command to execute the order reach the order first? And which was the case here. The close command reached it, and the order was executed before the cancel command reached it, and the order was reversed. Both of the clients ultimately actually see that the order was reversed, meaning it executed and canceled afterwards. Let's run this again, see if we actually see the opposite state again. We're seeing again, order opened was already opened, seeing 2 order items. Both of the clients see the exact same thing. it looked like here, okay, the command to close the order, to execute it, actually beat the call to cancel the order again. Let's execute this one more time. Maybe we'll actually see the race condition play out the other way around. This really is just like millisecond race conditions. So in this case, we actually see the cancellation won the race. So order was actually canceled, and the execution saw that the order was already canceled. So again, like even though we're concurrently heading two geographically distributed endpoints, we're always seeing things sort out in a consistent manner. There's under no circumstance any sort of inconsistency introduced by async replication lag windows. Let's now actually look at how things behave under failure. So to illustrate that a bit better, we have a few orders executing in a loop here. In the window here at the top, we can see one of those hopping between east and west regions, so making a call to east and west randomly. We have one loop executing orders against east and one executing orders against west. So let's actually wait for a nice point when maybe east is just adding a few order items, and then we're going to kill our east cluster. That worked well, good. Let's actually see what happens here. It was happening at a very interesting point. So we shut down the nodes in the east region just at the moment when this was trying to reach an order. So we actually see a message that the connection was closed before the message completed, which means we don't really know, did the order make it through or did the order make it not through. We can see that Restate retries against West 1 and the order goes through, and when we actually verify everything is correct. And that's just because Restate understands how to do idempotency of requests. The clients here implicitly just add a random number to each request that on retries they keep it constant, and then even though you retry against different regions, Restate actually deduplicates based on these request identities, idempotency keys really. So we can also see the other nodes in west just keep operating. We see in the top window here, whenever it tries to make a call to east, that one obviously fails because we just shut down the node there, and then it retries on west and keeps hitting west, and things just continue. We can also bring up this loop here again and just go with the failover scenario here again. After we can't hit east, the client just keeps hitting west for the remainder of this order. Let's actually take a look at the Restate cluster. What does the Restate cluster tell us? If we look at Restate CTL status, first of all, it tells us here's a dead node, node number 0, last seen a minute and 42 seconds ago. And we'll also see that because we have only 2 nodes left, we only have two partition processors attached to each partition, a leader and a follower, between nodes 1 and nodes 2. If we go to the log, we can actually see something interesting here, that for some of the loglets we get an epoch bump. We can also see this here. Some of them are in epoch 1 and epoch 2. An epoch bump here also is an indication that a leader of that particular partition moved away and a new leader took over, which means we're getting actually a new subloglet with a different ID. Good. Finally, let's actually try and bring everything back up again and see how everything just recovers. So we're going to start US East 1 again, and let's actually hope that DNS is quick enough to pick this up. And we should see that after a while, at least, once we start trying to hit US East 1, these requests go through again. So once this bottom script here, for example, is done with one iteration, it starts hitting US East, and we should actually see those continue again. Very well. So a node in East actually came back and is processing our requests. That's great. We can see the same thing in the script above. Here we're hitting west, we should be hitting east at some point again, and it should just work like we're bouncing between east and west. Here we go. We're also hitting east endpoints, and it works. Looking at the state of Restate CTL here, we can see no longer dead nodes anymore, and we can see there's 3 partition processors again on every partition, a leader and 2 followers, and we're basically back to a functioning 3-node setup. That's it.